So, welcome you all again. So, let's move forward. So, our next speaker is Dr. Ali Raza from Abdus Salam School of Mathematical Sciences, Government College, University, Lahore, Pakistan. The title of his talk is Interpolative Contractive Results in Metric Spaces. So, let's welcome him and over to you.
Thank you so much, Ms. Megha Pandey. And also, I am very thankful to the organizers that they give me chance to deliver the talk on this international platform. So the title of my talk is Interpolative Contractive Results in Metric Spaces. So as after a Banach fixed point theorem, there are many extension of such results, like many authors extend it in the for different type of contraction, and they also extend in shape of different distance structures. So the basic work which I will present here, it is related to the interpolative contractive mappings. So Krapina is the first who developed the idea or presented the idea first time of interpolative Canaan type contractions. So and he give he proved the fixed point results for that interpolative Canaan type contractions, and then later on this result has been extended by different authors in different metric structures, like as ordinary metric spaces, and then partial matrix. There are extension of different extensions of matrix, like ordinary metric spaces, M metric spaces, partial metric spaces, and so on. So in this talk, so there are three main sections. So first I will discuss some different distance structures, including partial distance structure or partial metric spaces, and then M metric spaces. And then later on, I will discuss different results related to the Canaan type contractions, interpolative Canaan type contractions in these metric structures. So firstly, I will discuss the results when our corresponding contractions are single valued. And secondly, as Nader extended the concept of Banach into the set valued mappings, so where he defined the he used the construction of the Hausdorff distance structures. So the last section of my talk will be related to that, where I will present the results of multi-valued interpolative Canaan type contraction, which are basically developed for Hausdorff distance structures. And in that case, I will also give the construction over the M matrix spaces. So M matrix spaces are basically the more generalized one, which are extending the concept of ordinary metric spaces, partial metric spaces, and then we are moved to M metric spaces. So the first part of my talk will be related to the different distance structures. So as we know that for a metric space, we need three conditions, like the non-negativeness and symmetric property, and then triangular inequality. But the author extend this construction into an more feasible ways, where they provide the results that the first condition can be extended like this way. Like if the corresponding values are same, and then he used the second condition, and then symmetric property, and then somehow generalized ones of the triangular inequality. So if we take D, our ordinary metric space, instead of this partial, so we can get it appears as the special case of this partial type of structure. So then they develop the result for this partial metric spaces. So here is the corresponding analogous of the Banach contraction principle. So in Banach contraction principle, we know that if there exists some constant lies between 0 and 1, then the corresponding single valued mapping has a fixed point. But in that case, so when they are extending the concept of metric, so they replace this metric with a partial metric, and if a similar type of constructions hold, then the corresponding mapping also have a fixed point in that partial metric spaces. So similarly, another extension of the metric is in the form of a M metric spaces. So here we can see that the first condition is similar to the that which is used in the partial metric spaces, but there is a difference between the second and fourth conditions. As in second condition, we have this relation that the distance between two elements is less or equal to the distance between same elements is less or equal to distance between any second element. But here this sense is replaced by another factor, which is called minimum of both of these two quantities. So similarly, we have the concept of symmetric, and then the triangle inequality is extended like this way. So on the similar patterns which appeared in the partial metric spaces, as they are extending the concept of the ordinary metric. Similarly here, this M metric is extending the concept of the partial metric as well. So we can say that every ordinary metric space is a partial and M metric as well, but converse may not be hold in these three settings. So moreover, a similar extension of Banach result has been find out in this structure. So if there exists a mapping which satisfies this condition, like this is the analogous of the Banach contraction, which it appears. So here we are using M metric instead of the ordinary metric. So if a mapping satisfies this contraction condition, and for some constant lies between 0 and 1, then such mapping have a fixed point in that corresponding complete M metric spaces. So next is the understanding of the Hausdorff metric. So this is the sense which I discussed. It is about the distance between points. So when we have a distance points, we can elaborate the distance by using ordinary metric spaces, partial metric spaces, or maybe are by M metric spaces. But when if the corresponding space is consist of sets, so then there is a concept of the Hausdorff distance between lies between them. So I will start from the Hausdorff distance for sets of partial metric spaces. So if we have two sets which are the subset of a partial metric space, then we can define a distance between them with this maximum of these two quantities. So here this is the supremum from elements of that set, and secondly this is the distance from the set. But here one thing is, remember that here we are talking about in sense of the partial metric. This is not, although the structure is similar, but the things are constituted in the sense of the partial metric spaces. So this is the sense of the distance between two sets. So if this is defined, then by using this construction we can define the set valued mapping. So in this way, the concept of Banach or the concept of single valued mapping can be extended to the set value mapping. So when we talk both of the things at the simultaneously, like extension of distance and extension of mapping, so it means that now we are in a structure which is extending both the senses, the distance sense and the mapping sense as well. So here is the extension of Nadler's fixed point theorem. So as we know that Nadler extended the Banach fixed point result to the set valued mappings. So when we talk about, but it was for ordinary metric structures. So when we talk about this extension in with respect to partial metric spaces, so we can say that the corresponding results of Nadler extended in partial metric spaces like this way. Here we have left hand side is here basically phi and lambda. These are the two basically set valued mappings, and here CB denotes the collection of all closed and bounded subsets of a partial metric space. So if phi and this lambda, we can say it satisfies this condition, so then for some constant lies between 0 and 1, then this mapping phi has a fixed point. So surely here the concept of fixed point is basically like that, that the element belongs to the corresponding set. So now the similar extension is appeared in the case of the M metric spaces when we need a construction of set valued mappings over M metric structures. So we need the Hausdorff distance between these two settings. So let's say we have any arbitrary sets from the collection of closed and bounded subsets of the M metric spaces. So then we can define the Hausdorff distance with respect to the maximum of these two quantities. And here delta M is defined this way, and M this is basically the distance between point and set. So next is the extension of the previous result, or we can say this is the extension of the Nadler's fixed point theorem in the case of the M metric spaces. So if we have a similar type of structure like the Hausdorff distance between these two set valued mapping, this set value mapping, single set value mapping is less or equal to some constant time this quantity, then we can say that the corresponding set, the corresponding map has a fixed point in that set, which is basically the complete M metric spaces. So this is the extension in the set valued mappings or multi-valued case. So next, I will move toward the Canaan type contractions. So these are the extensions, basically extensions of the Banach fixed point sets. But later on, as we know, there are many different contractions, Canaan type contractions, and like Suzuki type contractions, and so on. So my basic focus on this talk in this talk will be the results in the interpolative Canaan type contractions. So this contraction first time introduced by the Krapinar, and it basically generalized the idea of, or we can say, connect the idea of Canaan with interpolative exponents. So here I will discuss all the possible three cases depending upon the interpolative exponent. First, when the sum of the interpolative exponent is equal to 1, and secondly, when the sum of the interpolative exponent less than 1, and third, when the sum of the interpolative exponent is greater than 1. So firstly, we have a result where phi is any self-mapping and on a complete metric space, and it is said to be interpolative Canaan type contraction if it satisfies this condition for all such elements which are not basically the fixed point. Because if anyone is the fixed point, then we can get the value probably is zero. So it seems like distance is less or equal to zero, which does not make sense. So that's why we need this condition over all such values of the space where it is not basically the fixed point. Then and here fix of phi denote the set of the fixed point. So if a self-mapping satisfies this condition, or we can say that interpolative Canaan type condition, so then over a complete metric space, then it guarantees the existence of the fixed point. So here is the result for a metric space considered as self-mappings. The mapping is called interpolative if there exists constant, and these secondly is the result basically the case when the sum of the interpolative exponent is less than 1. Basically, this first theorem is related to the case when the sum of the interpolative exponent is get equal to 1, and this is for less than 1. So if we have a complete metric space and we have a self-mapping and the sum of interpolative exponent is less than 1, so in that case, the corresponding self-mapping also has at least one fixed point in that complete metric space. So next is the case when we have the sum of the interpolative exponent is greater than 1. So in that case, let's say we have a self-mapping phi, which is defined from a complete metric space to another complete metric space. So if it satisfies this condition, like the distance between their images is less or equal to this quantity where this is a constant lies between 0 and 1, and also the sum of the exponent which are on this metric, if this sum is less or equal to 1, so in that case we need the existence of some we need some more assumption, extra assumption, which is basically if there exists a point in this metric that satisfies this condition, then in that case, this self-mapping attains a fixed point. So this is the third case. So basically there are three cases. One is the sum of interpolative exponent equal to 1, less than 1, and greater or equal to 1. So in these three structures, the corresponding self-mapping have a fixed point in the metric space. So next, I will discuss this concept for two mappings, like the sense of the common fixed point. So let's say if we have a complete metric space and psi and phi be two self mappings, and if there exists a constant, so here is the case when we can extend the concept of interpolative Canaan type contractions into the sense of two mappings, like when we need the corresponding common fixed point result for the common fixed point result for the mappings. So in that case, we have this type of structure like if we have psi and phi two mappings, and there's some of the exponent is we can see that it is equal to 1. So in that case, it has a shared fixed point, or we can say common fixed point, if it satisfies this interpolative Canaan type contraction. So next is the case when the sum of the interpolative exponent is less than 1. So in that case, the extended definition is like this way. If a pair of mapping is said to be satisfies the interpolative Canaan type contraction, if there exist constants rho and gamma whose sum is less than 1, and it satisfies this condition, So then we can say that this satisfy chi rho gamma interpolative Canaan type contraction. So if a pair of mappings has this condition, like interpolative Canaan type contraction or conditions, and then over a complete metric space, then we can say that these two mappings have a common fixed point. So next result is uh, so next result is the extension of the previous result in the case for the class of the M metric spaces. So let's say we have a M metric space, and let's say psi and phi be two self mappings, and we call it this pair of mapping is said to be an interpolative Canaan type contraction pair if there exists a chi, we can say there exists a constant lies between 0 and 1, and there exists some rho which basically appears as the exponent. So we can say that this pair of mapping is said to be a pair of interpolative Canaan type contraction if it satisfies these conditions. So now we are talking about this construction in more generalized structure, distance structure, which is basically the M metric spaces. So if there is a complete M metric spaces, and the psi and phi is the pair of interpolative M interpolative Canaan type contraction, then this pair of contraction has a common fixed point in this complete metric spaces. So next, this is an example which basically appears for the case when our corresponding distance structure is not an ordinary matrix. So we can see that generally we have when rho is equal to kappa, we can say that when elements are same, then the corresponding distance is zero. But here in when we are talking about partial metric spaces or maybe M metric spaces, so in that case this does not happen. So this basically it's generalizing that distance structure. So in that case, here we choose this simplest example. So here we define distance like if both these elements are same, then we can take that element as it is. So here we define two mappings, like first one is this way as a piecewise function, and second one is the piecewise function, and we choose the exponent 1 over 2. So obviously the second one also 1 over 2, and the constant which is we need less than 1, we choose this 17 over 18 as a constant. So by using these conditions, we fulfill are the corresponding mapping has a common fixed mappings have a common fixed point in the complete metric space, which is basically the M metric space. And second one is the basically example of the case. Another example for this case, here we also choose a M metric space in this way. So we can see that here A is a greater or equal to 0. So whenever A is greater than 0, so it means that it does not satisfy the usual metric conditions. So in that case, we define the mapping like this way, and these are the interpolative constants, like this is 3 over 4 and 1 over 2, and in that case, this pair of mapping has a common fixed point in this metric, which is basically 0 to infinity. Set is basically 0 to infinity with this M metric defined on this set. So next is the case when the corresponding sum of the interpolative exponent is less than 1. So in that case, we can say that a pair of mapping, so again this construction is in M metric spaces, so a pair of mapping psi and phi is said to be chi rho gamma M interpolative Canaan type contraction if there exists some constant lies between 0 and 1, and some exponents rho and gamma whose sum is less than 1. So in that case, if it satisfies this condition, so then we can say that it is a this pair of mapping is a M interpolative Canaan type contraction pair. So if for a complete, and here we have the condition when the sum is less than 1. So for a complete metric space, if this pair of mapping satisfies this M interpolative Canaan type condition, then this it attains at least one common fixed point in this complete metric space. So here is the example, which is basically for the case when the sum of the exponent is less than 1. So here we choose these two exponent 1 over 2 and 1 over 4, and basically this appeared as our contractive constant. And here we use this metric structure, which is basically not ordinary distance structures, and we use these mappings, and it satisfies the basically this pair of mapping satisfy interpolative Canaan type contraction conditions, and consequently by using the above result, it have a common fixed point. So next is the case when the sum of the interpolative exponent is greater than 1. So in that case, the corresponding pair of mapping if this satisfies this condition, we call it, this is a pair of interpolative Canaan type contraction pair. And secondly, if there exists some point from this space which satisfies such that its m distance is less or equal to 1. So here we have an additional condition for existence of point in this space. So if such type of point exists, so we can say that this pair of mapping has at least one common fixed point in this complete metric space. So secondly, here is the example which appears as the case of when the sum of the interpolative exponent is greater than 1. So here we take here we use the exponent like rho is equal to 1 over 2 and gamma is equal to 3 over 4. So we can clearly visualize this, that their sum is greater than 1, and here we use this contractive constant. And thus by using this M metric structure, we can say that this for these two mappings psi and phi, it is basically a pair of contractive mappings, basically interpolation Canaan type contraction. So by using our previous result, it has a common fixed point in this metric space. So next is the case when we will talk about multi-valued interpolative Canaan type contraction. So before that, all of the results are discussed for single valued, when a mapping is moved from same set to this same set, or we can say as same metric space to metric space. But next we will move toward a construction of the our existence of the fixed points in the case when the mappings corresponding mappings are the set values, or we can say that the multi-valued. So here we need some different type of extension of that result, and obviously these extension exist in the for the case of Hausdorff distance structures. So in that case, a mapping here phi is a set valued mapping. It is said to be a multi-valued interpolative Canaan type contraction if there exists some contractive constant and an exponent such that this condition holds. Here left side is the basically Hausdorff distance, and this delta represents this distance from a point to a set. So if this if a pair of mapping satisfies this contractive condition, or we can say that interpolative Canaan type contractive condition, we call it. So then this pair of mapping has a fixed point, or we can say the common fixed point. So whenever we talk about a complete metric space and phi is, sorry, here we don't have a pair of mapping. This is a single valued mapping. We can, sorry, not single valued. This is a single mapping. Next, we have a pair of mapping result. So this phi is multi-valued mapping. So if it satisfies this interpolative Canaan type contraction condition, so we can say that it has a fixed point in this complete metric space. So next is the result for the case when the result of single value is extended to the case when the sum of the interpolative exponent is less than 1. So in that case, if phi is a set valued mapping which satisfies a interpolative Canaan type contraction or contractive condition, which is basically this one. So it means that this Hausdorff distance can be controlled by this quantity. So here is the result for a complete metric space. If basically this is the basically definition for the case when the sum of the interpolative exponent less than 1. So in that case, if we have a complete metric space, so the corresponding mapping, the set valued mapping, has a fixed point. So next is the result for a complete metric space. Consider multi-valued mappings. We have two multi-valued mappings, phi and psi, and if these are compact mappings, basically compact sets for every rho and kappa belongs to, these are basically elements from the metric space, and there exists a contractive constant. If it satisfies this condition, then we can say that this pair of mapping is said to be interpolative Canaan type contraction pair for multi-valued mappings. So next is basically the definition for the case. I think this is a mistake. I think here we have a single valued result basically. Okay, so here is the case when we have a pair of mappings. So this pair of mapping is said to be interpolative Canaan type contraction pair if it satisfies this condition, and it has a common fixed point if we are talking about in a complete metric space. So let's say in a complete metric space, if this pair of mapping is a M interpolative Canaan type contraction pair, then these phi and psi have a common fixed point in this complete metric space. And here is the example. So as we discussed earlier, that when we are talking about multi-valued mapping, so we need sets. So that's why these two mappings are set valued. So here we used like whenever this elements belongs to this set, then the corresponding values appeared as a set. So when we have this type of set construction, and for this value of exponent and this contractive constant, and for this any value from the of a lies between 0 and 23, then this corresponding mappings, these two corresponding mappings have a common fixed point. Next is the case when the sum of the interpolative exponent is less than 1. So in that case, a similar type of structures appear, but here we need extra conditions on our mappings, like the distance between minimum distance between the points and the set must be greater or equal to 1. So in that case, if this condition exists, so we call this pair of pair of mappings as an interpolative Canaan type contraction pair for the case whenever rho and gamma are corresponding exponent is the sum is less than 1. So in that case, if we are talking about this structure over a complete metric space, complete M metric space, so this pair of mapping has a common fixed point. So here is the example where we can talk about we can take this set and define metric on it, and then we are defining the set valued mappings like this way. Here this is the basically closed and bounded set, this is also closed and bounded set. So in that case we are choosing the contractive constant 3 over 4, and the basically exponent, one exponent is 1 over 2 and the second exponent is 1 over 4, so their sum is basically less than 1. So in that case the sum is less than 1, and by our previous result, it assured the existence of the common fixed point for these two mappings. So next is the last case of this construction. So let's say cyan 5 by 2 multi-valued mappings, which are or we can say set valued mappings, and here the sum of the interpolative exponent is greater than 1. So we call this pair of mapping as a interpolative Canaan type contraction pair if there exists two exponent lies in this interval. Also, we are talking about the sum is greater than 1, but still we are talking about a controlled sum, because if it is sure toward infinity, so surely we cannot control the things. So then we are not talking about that situation. We are just talking about when these lies to. So we can say that this sum is maximum greater, lesser, maximum sum is greater than 1, but surely less or equal to 2. So in that case, if this condition is hold, that is the household distance is controlled by this quantity. So in that case, we can say that if a pair of mapping satisfies this interpolative Canaan type contraction pair, and here the sum of the interpolative exponent is greater than 1, and there is an additional condition, at least we have this such type of point, existence of such point. If this point exists, like the distance from point to the set is less or equal to 1, then in that case, these two mappings have at least one common fixed point. So here is the example. So here we take a M metric space, and
Hello.
secondly, we use the
Sorry to
contractive
interrupt.
constant. Sorry,
Sorry to
contract.
interrupt, but only have 3 minutes.
Yes, yes. This is last slide. This is last slide. Okay. So we have rho and gamma is equal to 3 over 4. As we can see, this sum is greater than 1. So the previous theorem guarantee the existence of common fixed point in this case. So here are some papers, references, and some in this talk, most of the results are presented from the work which I have done with my students. So you can see the references here. So here are some more references. Thank you so much. So any question?
Thank you so much for the talk. So now I would like to request to the audience if they have one or two quick questions for the speaker. So if not, let us thank the speaker. So our next talk will be in 2 minutes.
Okay, thank you so much.